The next category of hydrocarbons are aromatic hydrocarbons. They are also called arenes. The reason being they have a very specific smell, the aroma, that is why they are called aromatic or arenes. Now the arenes can be of two types. They can be like benzenoids and non-benzenoid. Benzenoid means they are like benzene or they have benzene in them. It can be normal benzene, it can be your naphthalene. This is what we have is naphthalene. This is benzene. If we have two benzene rings joined to each other, we call it biphenyl. So all these are benzenoids, arene. Non-benzenoid includes those which are actually not like benzene. Like we can have this one. This is called furan. We can have with sulfur, which is called thiophene, etc. So this is what we have the general characteristic classification. Now let us do their nomenclature. And let us do isomerization in these compounds. See, we call benzene, since all in the benzene all 6 carbons are similar, we can't differentiate them from one another. We can start the numbering from anywhere. So if we have a 1-methyl attached to it, it's called methyl benzene, or it's called toluene. If we have 2 methyl groups, we can call it 1,2-dimethyl benzene. We also call it orthoxylene. Xylene is the benzene which is having 2 methyl. Ortho means what? We need to know this. When benzene is having 1 group attached to it, and if we start numbering from it in a clockwise way, the position number 2 and 6 are called ortho. We give a symbol O in the common nomenclature system. The position number 3 and 5 are called meta. We give a symbol M. And the position number 4 is called para. The symbol is P, opposite. So when we have, if this is taken major one, the next one is ortho to it. That's why it's called orthoxylene. So this is how we name them. And therefore, if anybody says like I'm having paraxylene, so it's very obvious that we are having 2 methyl, which are actually our para positions with respect to each other. So this is paraxylene. This is what they show. And you need to also remember, therefore, this para, meta and ortho, they will be your position isomers. So they mainly show position isomers because they can't show any other, because then no other, almost impossible is there to have any other molecule with such a formula, with C6H6 formula. So they mainly shows position isomerism. Now let us see the structure of benzene. See, benzene is having a formula of C6H6. It's a ring, carbocyclic ring, on which what we can have is, its 2 Caccoli structures are there, which are drawn like this. Now how we reaches to this structure is, we need to know that in this carbocyclic ring of 6 carbons, all these 6 carbons are sp2 hybridized. All of these are sp2 hybridized. So they are trigonal planar. Once they are trigonal planar, this makes this whole molecule planar. So benzene is, remember, is planar. Moreover, since they are sp2 hybridized, each one of these are having what? Unhybridized sp2 hybridized orbital. Sorry, pz orbital. Now these pz orbitals, they get sideway overlapped from with the neighboring pz orbitals, and this gives this molecule what the delocalization of the pi electrons. This p orbital can overlap with this also and with this also, and that is what makes these 6 pi electrons to get completely delocalized all along the ring, and that is what makes it more stable. So there's a complete delocalization, and as a result what we do is we represent it by its 2 canonical structures. The double bond can be here. If I number it, it can be like this. The double bond can be between 1 and 2, 3 and 4, and 5 and 6, or it can be between 2 and 3, 4 and 5, and 6 and 1. So any one of these. That is why we represent this molecule with a hybrid structure. We put a circle at the center of it, so in order to show that there's a complete delocalization of the pi electrons all along the 6 carbons of this cyclic structure. Now, but we nowadays we prefer to represent it by any one of these canonical structures, because we know that at least for a fraction of a second these structures are existing in the nature. Somehow they are most closest to the actual benzene which exists in the nature. That is why we prefer to represent them by these structures. Now, due to delocalization in benzene, the bond length also gets changed. We know that the CC single bond is 1.54 Angstroms unit. C double bond C is actually 1.34 Angstroms unit. But what we find is all CC bond lengths in this benzene are of this are of 1.39 Angstroms unit, which we call it a partial double bond character. So it's neither a single bond nor a double bond, it's a partial double bond, and it is mainly because of the delocalization of pi electrons. Now, after understanding the structure of benzene, now let us discuss what is exactly the aromaticity is. See, those only carbocyclic rings will be called aromatic, or will be showing aromaticity, which will follow the following conditions. The conditions are very specific. They have to be planar. They must have a conjugated system for complete delocalization of pi electrons, and the third and the most important, they follows Huckel's rule, which says they must have 4n plus 2 pi delocalized electrons, where this your n is any integer. It can be 0, 1, 2, 3. Now let us see the examples which follows these conditions. The examples include like benzene. In benzene, when n is taken as 1, we have 6 pi electrons. We have naphthalene. Because in this case n is 2 and we have 10 pi electrons. We have anthracene. Where n is 3 and we have 14 pi electrons. So this is how we have aromatic compounds. Now let us see the preparation of benzene. Benzene can be prepared first from alkynes by its cyclic polymerization. We know that when acetylene is passed through red hot copper tube, what we get is benzene. So that's the first method of preparing benzene. We can also prepare benzene from aromatic acids, like we have this one which is called benzoic acid. We do this by decarboxylation. See, if we remove this COO, that means CO2, we get a benzene. And we know that decarboxylation is done by heating it with soda lime. What we get is benzene plus Na2CO3 plus H2O. So very easy way of preparing benzene by the decarboxylation of aromatic acids. The third way or third method of preparing benzene is from phenol. We can take phenol, it's a redox reaction, remember, and we can heat this phenol with zinc dust. The zinc gets oxidized to zinc oxide and we get benzene. So these are the methods of preparing benzene. Now let us see the properties of the aromatic hydrocarbon, the benzene, which we have in our syllabus. Let us see first its physical properties. The aromatic hydrocarbons usually are non-polar, colorless liquids or maybe solids, but having a very characteristic smell or aroma. You must have seen the naphthalene balls. They have having a very specific the naphthalene or moth smell or moth aroma, which makes them very, very easily distinguishable from the rest of the other compounds. Other important thing about these are that since these are non-polar in nature, they are completely completely immiscible with the polar solvents like water, but yes, they are soluble in the non-polar solvents like CCl4, carbon disulfide, etc. Now let us discuss their chemical properties. Chemical properties. The chemical properties of aromatic hydrocarbons, mainly the benzene, includes the electrophilic substitution reactions. See, we know that we call them SE reactions. You need to know this. Though they are having a high electron density because of the delocalization of pi electrons, they doesn't show the addition reactions very, very easily. The reason is because if they show addition reaction, they will lose the aromatic character because of the loss of the pi electrons. And that is why what we find is that they only show substitution reaction, and that too electrophilic, because nucleophile cannot approach any benzene ring, and because it gets strong repulsion from the negative charge of negative charges. So they show mainly the electrophilic substitution reactions. We have basically 4 types of electrophilic substitution reaction which are shown by benzene and its derivatives called nitration, sulfonation, halogenation, and Friedel-Crafts alkylation or acylation. Let us start our reaction with nitration first. Now let us see the nitration of benzene. When benzene is reacted with nitric acid in presence of sulfuric acid, the product obtained is called nitrobenzene. This is the product which we get, which is called nitrobenzene. And this reaction, this introduction of nitro group on benzene ring is called nitration. So this is what we have, nitration of benzene. The mixture of HNO3 and H2SO4 is called nitrating mixture, because this is a mixture which gives us nitronium ion, the electrophile, because of which we get the nitrobenzene. The next electrophilic substitution reaction is sulfonation. It is the introduction of sulfonic SO3H group on the benzene ring. It is done by heating benzene with fuming sulfuric acid, which is H2SO4 having excess of SO3, and this results in the formation of sulfonium ion which gets attached to the benzene ring, and we get benzene, sulfonic acid and water. So this is what is called sulfonation. The third electrophilic substitution reaction is halogenation. It's the introduction of halogen. It is done by reacting benzene with chlorine in presence of anhydrous AlCl3 or FeCl3. This gives us chlorobenzene and HCl. In a very similar way, if we react this with bromine in presence of Al Br3, we will get bromobenzene and HBr. So the introduction of this chlorine or a bromine or halogen on the benzene ring by this through the electrophile like chloronium ion or bromonium ion is called the halogenation. The next electrophilic substitution reaction is Friedel-Crafts alkylation. It's the introduction of any alkyl chain or alkyl carbon on the benzene ring is called Friedel-Crafts alkylation. This is done by reacting alkene with any alkyl halide. The alkyl group which we want is to be taken in the form of alkyl halide in presence of anhydrous AlCl3 or AlBr3. Let us take here methyl chloride. So what we get in this case is a methyl benzene or toluene plus HCl. So this introduction is called of the methyl group on the benzene ring is called Friedel-Crafts alkylation. If we take in this place CH3, CH2Br, AlBr3, what we get on this benzene is CH2, CH3, ethyl benzene plus HBr. So that is most important to note in these cases. The next reaction is called Friedel-Crafts acylation. Now what is this Friedel-Crafts acylation is? It is the introduction of the acyl group or C double bond O group. This group is called acyl group. Now how it can be done? It is done by reacting benzene with any acyl chloride, like we have taken acetyl chloride in presence of course anhydrous aluminium chloride, and the product obtained is a ketone which is called acetophenone, of course plus HCl, or it is also called phenylethanone because acetophenone is its commercial name. So by taking any acyl group with anhydrous aluminium chloride, yes, we can introduce the acyl group and we can have the acylated product. That is why this reaction is called Friedel-Crafts acylation, and in this case, since we are using acetyl chloride, this particular reaction is called acetylation. We can also use in place of acetyl chlorides anhydrides, like if we are taking like acetic anhydride. Acetic anhydride can also be used in AlCl3. What we get is acetophenone plus HCl, and of course the other product obtained is, in this case, is your acetic acid. Is going to give us the other product is acetic acid. So this is how what we get are the different products and of the acylated products. If we are taking either acetyl chloride or we are having the anhydrides, the same reaction takes place. Acylinium is the electrophile which is being generated out, and this is what happens is they attack on the benzene ring and we get the hydrogen substituted, and this is what is the product obtained along with the acetic acid in the Friedel-Crafts acylation if we are taking acetic anhydride. Remember, in these electrophilic substitution reactions, like we were doing halogenation, if the excess of chlorine or the reagent is taken, what happens is all the hydrogens of the benzene can also be can be substituted, and like in this case, if it is allowed to take place and carry on its own, what we get is this product. All hydrogens gets substituted like this, and the product obtained is called hexachlorobenzene. It is called hexachlorobenzene. It is C6Cl6. That is the formula of this compound is. So this is what you need to know. Now let us see the mechanism of the electrophilic substitution reaction. See, the mechanism mainly involves the most important step is the formation of the electrophile. Now let us see how it gets formed in the different reactions. In case of halogenation, we are using the Lewis acids, anhydrous Lewis acids like aluminium chloride or ferric chloride. Now they, since are having 6 electrons, they accept one chlorine with the pair of electron. This gives us what? Chloronium ion and AlCl4 minus. So this is how the chloronium ion gets generated. So this is what most important thing to note in this case. Now let us see in this case, in case of halogenation, like we have done in case of halogenation. Now let us take acylation. In case of acylation, we are still taking any acetyl chloride or acyl chloride in presence of aluminium chloride. This aluminium chloride is anhydrous, it is Lewis acid, it accepts this chlorine with the pair of electron. So what we get is this CH3C double bond O plus, which is called acylinium ion, and in this case I can call it acetylenium ion because this is acetylenium ion. It's a general name, and plus AlCl4 minus. So this is how this acylinium or electrophile is being generated. In alkylation, like if you are having methyl chloride, we again take it in presence of anhydrous aluminium chloride, which acts as a Lewis acid, accepts the chlorine with the pair of electron, giving us what methyl electrophile and AlCl4 minus. So this is how the electrophile is being generated out. Now let us see how we get nitronium ion in case of nitration. See, in case of nitration, what happens is two acids are taken. H2SO4 being a stronger acid releases H plus and HSO4 minus ion. Now what happens in this case is this attacks this is the nitric acid we have. This H plus attacks this OH group of this one, converts it into a water, which acquires then now oxygen acquires a positive charge. It withdraws electron and it gives us what? This nitronium ion and water. So this is how we get nitronium ion, which is the electrophile, our electrophile for the electrophilic substitution reaction. And the second step of the this mechanism is the attack of the electrophile. Attack of the electrophile. How it takes place, let me explain it to you. Like we have this benzene. Now this electrophile which is represented, it can be your chloronium ion, your nitronium ion, your acylinium ion, your methyl ion, carbocation ion. So what happens is, this is represented by E plus. If this pair gets shifted for a moment on this carbon, it attracts this electrophile, and as a result what happens is, the carbon number 1 which we have numbered like this one, has having now hydrogen as well as electrophile, and carbon number 2 acquires a positive charge. Now what happens is, the circulation or movement of this positive charge takes place. It will ask from the electron from this carbon number 2, or will ask for the electrons from carbon number 3, which withdraws this electron which it is sharing with carbon number 4. So the next resonating structure we can get is this one. Then it moves from here to this side, and the next resonating structure obtained is this one. So the positive charge moves from ortho to para, and then it comes back again to the ortho position. And then therefore what we write in a very simple language is that this is giving us what? The whole lot of positive charge all along the ring. The next step is the removal of the proton or H plus. Now what happens is, the next step is removal of proton. Now if you see the structure very carefully, what you find is the electrophile is attached here, where there is a positive charge at the carbon number 2 here, and we have this structure. Now this structure is unstable, it's not following Huckel rule, so this carbon number 1 immediately withdraws its electron from the hydrogen, so that the aromatic nature of this compound is restored, and what we have is being now electrophile is only left out at carbon number 1 and hydrogen is given out as a proton. So this is how the electrophile has substituted hydrogen, and we call these reactions as electrophilic substitution reactions. The aromatic hydrocarbons, they show addition reactions but under drastic conditions, extreme conditions of very high temperature, pressure, and even presence of catalyst. Let us see the hydrogenation. Yes, when benzene is reacted with hydrogen at a very high temperature and pressure in presence of a nickel, it gets converted into cyclohexane. So that's the most important thing, and 3 molecules of hydrogen gets consumed. Similarly, we can do its chlorination, which is again is a type of addition reaction. When this benzene is subjected to chlorination in presence of UV or diffused sunlight, what we get is chlorine on each carbon, and addition has taken place. Remember, it's a cyclohexane ring. We call it 1, 2, 3, 4, 5, 6 hexachlorocyclohexane. It is also called BHC, benzene hexachloride, a very important pesticide which is now universally banned because of its non-biodegradable nature. So these are its addition reactions. They also show combustion reactions. They also shows combustion reaction, and these, like if we take benzene, when they combust it with oxygen, it gets changed into CO2 and H2O. We can do it like this C6 H3 15, this is 15 by 2. So this is a general reaction, and of the combustion of benzene, they give CO2 and H2O on combustion. Now let us understand the direct influence of the functional group in monosubstituted benzene. See, till now we have seen that how we can introduce first functional group on benzene ring. Now after this, if you want to introduce one more functional group, definitely the reaction will be very similar. But yes, where they go, to which carbon they go, that is being decided by the functional group which is already present on the benzene ring as the first functional group. Now they direct the other incoming group electrophile to which carbon they will go. And on that basis, we classify these functional group as one which direct them towards ortho and para positions, and the one which direct them towards meta position. So let us first see ortho para directing groups. See, these are the groups, like let me give you the examples. We call them, these are OH group, OR group, NH2 group, secondary amine, tertiary amine, amide through nitrogen, esters through oxygen. All these are called electron releasing groups. They show plus R effect and they releases electron towards benzene ring. I can show you with one example. And what makes them very different is that the atom through which they are attached to the benzene ring, all those atoms are having some lone pairs. That is why these lone pairs gets readily transferred to the benzene ring, and that is why these groups always are called orthopara directing groups, and they are also called ring activating or stabilizing groups, because we know that benzene is an electron withdrawing group itself. It shows minus I effect. So if any group, any species is giving electron to it, it stabilizes it. Let me explain it to you with example of phenol. Like in case of phenol, what we find is like if this bond gets shifted to this carbon, the oxygen donates its one lone pair, and this is how it acquires a positive charge because it has given its one lone pair, and the negative charge comes at ortho position. Now this gets transferred to the next carbon, through which it gets transferred to para position like this. New bond is formed like this, We are having oxygen with positive charge. From here it shifts to the next carbon. From here it again comes to the ortho position, and therefore the next structure obtained is having what? A negative charge at ortho position. And a new bond is like this. So what happens is, again the bond comes here, the one pair goes back to the oxygen, and the next resonating structure which we get is very similar to the first resonating structure, with the only difference is that the position of the double bonds has been changed. Now these structures shows that there is a high electron density at ortho and para positions. That is why whenever this OH group or containing benzene, which is called phenol, will be showing the second substitution reactions, electrophilic substitution reactions. The electrophile will be attacking both at ortho and para positions. Of course, para products will be the major product, the reason being because they will be more symmetrical. But yes, both products are formed because of the high electron density at ortho para positions. And all these structures follows Huckel's rule, and that is why these groups are called ring stabilizing, activating groups, and they are ortho para directing groups. Now let us see the meta directing group. The meta directing group includes nitro group, sulfonic group, acid group, aldehyde group, ketone group, ester group, cyanide group, etc. All these groups, they are also called electron withdrawing groups. They show -R effect. They are called ring deactivating groups. The reason being because they deactivates the benzene ring, takes out electron and tries to break down its aromatic nature by not allowing it to follow Huckel rule, and that's why they are called meta directing groups, because they will create positive charge at ortho and para position, so the incoming electrophile will be coming only at meta position. Moreover, since the positive charge is created on the benzene ring, they will be showing this electrophilic substitution reactions with difficulty under extreme conditions. Now let me explain it to you one of these in detail. Like, let us take this example of nitrobenzene. In this nitrobenzene, what we find out in all these groups, what we will find is that the atom through which they are attached to the benzene ring, those atoms will never be having any lone pair. Rather, what we find is that they will be bonded to more electronegative atoms. So oxygen will withdraw electron towards itself because it's more electronegative. So in that case, nitrogen will try to take out electron from benzene. So in this case, what happens is ortho position acquires a positive charge, because double bond is formed between carbon number 1 and nitrogen. Oxygen acquires a one pair extra, so it acquires a negative charge. Other things are very similar. Now this carbon at ortho position becomes deficient. It asks for the electrons from this next carbon. So this positive charge gets shifted to what? Para position, like this. These are the lone pairs I am drawing. From here it again shifts to what? The ortho position, like this. And then it comes back here in this way. So the last and the fifth resonating structure which we draw is very similar to the first one, with the only difference is this, that the position of the double bond in the benzene ring has been changed, which shows that the complete movement of the lone pair pi electrons is taking place, or lone pair electrons is taking place. And you can see here in these structures 2, 3 and 4, there is a positive charge at ortho and para position, so we can't expect the coming electrophile to be coming at ortho and para position. Rather, if they want, it is approaching, it will be approaching at the meta position, this position. That is why all of these groups are meta directing groups, and since they create positive charge, are not allowing the aromatic character to exist in these compounds, they are called ring deactivating groups. Carcinogenicity and toxicity. See, the benzene and the polynuclear hydrocarbons, which are having 2 or more than 2 rings, are found to be toxic in nature. They generally are not broken down in our body. They are the ones which starts getting accumulated in our body, and they causes cancer. They are carcinogenic in nature. They also damages the DNA of our body, and they can lead to some hereditary, very strong hereditary problems, very effective, which actually are giving not only the toxicity, but can lead to alteration in the genetic order and genetic diseases.